Oh my gosh, right from the beginning, a big old typo on this. This is the BC Winter Break Assignment 2022. I am so sorry about that. Um, you maybe remember a little bit about vectors and parametrics and polars, but maybe not. So we're going to take a look at this. So starting with this first one, if I have two equations and one's an equation for x and one's an equation for y, notice they have a third variable. And quite commonly, the third variable is t. Often these happen with respect to time. That's the most common application. We call these parametric equations. And so if we want to graph them and sketch a curve, a common strategy is to make a table of values. And I think you may not have seen this in your last class, so I'll go through what that means. And then eliminate the parameter is something also students may not recognize what that's asking you to do. It's not hard, but you may not recognize it. Okay, so what I'm going to do is I'm going to pick some values for t. Now, these are the values of t that I chose. Why did I pick these? First of all, a square root cannot be a negative, so that impacted that t needed to be no lower than -2. And then I also knew I was going to have to square root, and so I picked values of t that would give me integers to square root or positive numbers to square root that were whole numbers or perfect squares. So that's why I picked those. So if I took those values of t and I plugged them into x, I would get this blue row right here for my outputs. If I take those same values of t and plug them into the equation for y, here's what I would get for y. Now what we're going to do is we're going to graph on an xy coordinate plane. We have this third variable t, but we're not graphing t. We're going to graph these points. So the point 0, 5, 1, 4, 2, 1, and 3, -4 will be on my graph. I can't have anything to the left of that because this was the smallest value of t in order to make sure that I'm not square rooting a negative. So I am starting this at the t coordinate of -2, which corresponds to the ordered pair 0, 5. Now, the direction. If we go from the smaller inputs to the larger, this is moving in this direction. I'm just going to put an arrow on here. This last part, eliminating the parameter, what that's talking about is getting an equation that has x's and y's in it. An equation with only x's and y's and no t's. And so what you can do is you take one of your equations and isolate t. So if you take the first equation and you isolate t, you get this. If you then plug that in for t right here and simplify, you get this. Now, y is greater than or equal to 0. You can see that from the graph, and that's because, x is greater than or equal to 0. You can see that from the graph, that the x coordinates start at 0. All right, let's take a look at one of the actual problems from the assignment. So if we make a table of values and sketch a curve, we want to indicate the direction of the graph. This particular one gave us a range of values for t. That's not always true, but I'm going to go ahead and make a table. I will create 3 rows on this table, one for t, one for x, and one for y, and I'm going to pick the integers here on this interval. And I'm going to take these and I'll substitute them in. So if I take each of these inputs and I substitute them first into x, I'd get -2, 0, 2, and 4. If I take those same inputs and I substitute them into the equation for y and replace t, I'd get 1, 0, 1, and 4. And I'm now going to plot the xy ordered pairs on my graph. So I have -2, 1, 0, 0, +2, 1, and 4, 4. And so what this looks like, remember this one has only, the domain is totally restricted here. Looks like that. And the direction, if I go from the smaller inputs to the larger, is something like this. The last thing they want me to do is eliminate the parameter, which essentially means write an equation that have the variables x and y and not t. So if I isolate t in one of these, you can kind of pick which one, but I'll isolate t here. T is the same as x over 2. If I then take that expression and substitute it in to the equation for y, and I'll replace t with x over 2, then y is x squared over 4. Now we are in a restricted domain, and the domain restrictions are listed as x restrictions, and x is going from -2 to 4. Number 2. So for number 2, I don't have domain restrictions here that are given to me. And if I think about these equations, I don't actually have any values of t that would cause either x or y to be undefined. So what this means is that I could pick any values of x and y. So I'm going to pick a couple negative, maybe I'll squeeze in another column here. The old standby that you probably learned in Algebra 1 of -2 up through 2, and I'll just pick those integers. So starting with x, if I substitute in, let's see, I get -2, 1, 2, 1, and -2. If I substitute in for y, because y and t are the same, I can just repeat those values. And now I'm going to plot x, y points on an xy coordinate system. And so I have the points -2, -2, -1, -1, 2, 0. Oh, I'm just making sure I did that right. Okay. 2, 0, 1, 1. And I think I plotted that wrong. Hang on. This would be, oh, no, I guess I did that right. 1, 1, and -2, +2. And I think I graphed this wrong. So let me see if I can find my error in here. I plotted something wrong, or I calculated something wrong. So let's see. Oh yeah, this is a -1. -1. I guess I somehow figured out that I wanted a -1, -1. But oh no, it's not. This is a +1. Okay, so I plotted this point wrong. Let me redo that one as +1, 1, and let me make sure I didn't have any other situations like that. And let me just check my points again. All right, so -2, -2, 1, -1. I still plotted that wrong. I'm doing awesome. 2, 0, 1, 1. There we go. All right, now I've got my points plotted correctly. So what this ends up looking like, and I could plot some more points if I wanted to, but this one ends up looking like a sideways parabola. And it's a little bit weird in terms of like direction on this. But if we start with -2, if we start right here and we kind of trace the points, we started at this one, then we moved to this one, and then here. So if I kind of trace them through, I'm going through along this that way. You can draw that arrow in a different spot as long as you're kind of following the path. The equation here, I want to isolate t, it's already isolated, and I want to replace t. So x is 2 minus y squared. We typically isolate the y variable. So let me kind of reorder this a little bit. Y squared would then be 2 minus x. And you could leave it like that. In fact, probably commonly it would be left like that. I guess sometimes actually people could, since this is a sideways parabola, sometimes people do isolate the x. I think those are both really good equations. All right, now number 3, those are sine and cosine. So when I create my table of values here, I'm going to pick values of t that I actually know how to evaluate sine and cosine for. I'm going to pick some of my quadrangles. Okay, so I'll pick like 0, pi over 2, let's see, pi, maybe 3 pi over 2 and 2 pi. And, oh, by the way, I should mention that on Earl's website, we do have all of the solutions for these. And one of the things that's probably a little bit confusing when you first look at them is you might anticipate, oh my gosh, how am I going to graph these with 0, pi over 2? Those numbers are hard to tell. But keep in mind, you're going to be graphing x and y. This is a little preview of what that one's going to look like. Okay, so if I plug in values of 0, the sine of 0 is 0, so this one's -1. Sine of pi over 2 is 1, so 2 minus 1 is 1. Sine of pi zeroes out. 3 pi over 2 has a sine of -1, and then 2 pi zeroes out. If I do cosine, for the y equation, if I plug in as 0, the cosine of 0 is 1, plus 2 is 3. Cosine of pi over 2 zeroes out. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. and the cosine of 2 pi is 1. So I'm going to plot these ordered pairs on this graph. I have negative 1, 3, 1, 2, and negative 1, 1. Let me just check, make sure that that's right. And then I have negative 3, 2, and then back to negative 1, 3. This is an ellipse, something like that. And if I go from where I started at negative 1, 3 and kind of go around, you'll notice I'm going around this ellipse that way. All right, to isolate the parameter, this one's a little bit interesting. I'm going to switch over to the solution so you can kind of see. What you want to do is you want to solve for cosine of t and sine of x, and then we're going to substitute into this trig identity. Okay, so now that we've kind of talked about the strategy, we're going to try to apply that. So I'm going to isolate the trig function of sine and cosine. So on this one, the y minus 2 is the same as cosine of t. And on this one, let's see, x plus 1, and then all divided by 2 is the same of sine of t. And I'm going to substitute this into the trig function cosine of t quantity squared plus sine squared of t is equal to 1. So cosine of t is y minus 2 quantity squared. Sine of t is x plus 1 quantity squared divided by 2 quantity squared. I typically write it like that, and that equals 1. And that's our general form of an ellipse. We often write the 1 underneath there. So that you can see kind of how things are moving vertically and horizontally. You might remember you square root these from our little center point, and that's how far you move left, right, up, and down. All right, I'm encouraging you to pause the video for number 4 so that you can try this one on your own. All right, welcome back. I'll get this one started. So I'm going to create my 3 rows of t, x, and y, and I'm going to test my quadrangles at 0, pi over 2, pi, 3 pi over 2, and 2 pi. And I'll just plug in some values. So remember the cosine of 0 is 1. Is this the same problem? Oh, no, it's not. Okay, cosine of 0 is 1, so this is 1. Cosine of pi over 2 zeroes out. Cosine of pi is negative 1, and so forth. If I do those for y, I'm using same values of t and with 3 sine of t plus 1. So cosine or sine of 0 is 0. Pi over 2 is 1. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is negative 1. And sine of 2 pi is 0. I'll plot these xy points now. So let's see. X is 1, 1. The first point, the next point, negative 1, 4, negative 3, 1, negative 1, negative 2, and 1, 1. And again, we have this ellipse. And if I plot them in order from when t goes from smallest to longest, we're going around this way. All right, to go ahead and eliminate the parameter and write this as an xy equation, I'm going to go ahead and isolate sine and cosine. So from this first one, if I isolate cosine, I'd have x plus 1 all divided by 2 is cosine of t. And if I eliminate sine, y minus 1 all divided by 3 is the sine of t. And I'll do cosine squared of t plus sine squared of t is 1. I'll use that Pythagorean trig identity. So x plus 1 quantity squared over 2 quantity squared. Notice that becomes a 4. Plus y minus 1 quantity squared over 3 squared, and that equals 1. And again, that's my general form for an ellipse. You might remember the center is supposed to be at negative 1, 1. There it is. If you square root the x's, 2 tells you how far you would go in either direction, left and right. If you square root the 9, that tells you how far you would go up and down. All right. I'm going to finish this page, and then I will go ahead and pause the video and create a new one so it doesn't get too long, but for the next part. But I do want to show you on your calculator that you can graph in polars. You probably don't know that. So let me show you. I'm going to open up my calculator and sit and wait while it takes forever here. Sorry, as we wait. All right, so I'm going to go ahead and move to a graph. And what I'm going to do is I'm going to change this to polar. This, as you notice, is X and Y. So if I go to menu and I go to option 3, which tells me the different types of graphing, option 5 is polar. Now this is going to get you from 0 to 2 pi. All right, that's just written as a decimal. My first one was 2 cosine of theta. Make sure you don't type cosine, use the trig button of cosine. And then theta is, let me see if I can remember, I think it might be as pi. There we go. And then I can go ahead and hit enter and that'll graph that. So this is a circle. It's going to go across a diameter of 2 on the x-axis. Okay, so I'm going to just sketch this really quickly. So this is going to go across with a diameter of 2, and it's kind of symmetrical around the x-axis. That is awful. Let's see if I can do any better. I'm very sorry. I wish I were much more skilled at drawing circles than I actually am. All right, so if you anticipate what would 3 cosine of theta look like, you probably have some ideas. Let me see, toggle over here. I'm just going to go back to tab. And I'm just going to change my last one because it's still cosine. Let's see if I can. Yeah, I'll just change that to a 3. See what happens. You might notice it's still really a circle that's still centered around or symmetrical around the x-axis here. But now its diameter is 3. And you might also notice it goes like 1.5 above and 1.5 below. And again, that's because this is going to be symmetrical around the x-axis. So it's going to go from here to here. And I'll try my best to get myself some points here for frame of reference on this circle. Something like that. As a beautiful circle. All right. Try to anticipate what you think this one would look like. We will be graphing these without calculators this year. So you really do want to look for the patterns here. You don't want to rely on your calculator. But if I toggle back to the calculator, I'm going to tab to get to my entries. And I'm just going to go ahead and insert in here a negative. And let's see what happens. You might notice it moved to the negative side of the x-axis. However, it is still a circle that is with a diameter of 3. And it is still symmetrical around the x-axis. That is awesome. That was fantastic. That was the best circle I've ever made. Okay. Again, please be intellectually curious. How do you think sine will change this? And again, if you just graph these, I'll just graph one of them. And then from there, we'll just talk about patterns. I'm going to go ahead and delete out trig function here and switch this over to sine of theta. In case you missed where I entered theta, it's with the pi button to the left of h. And notice, oh, I did -3. Well, you can anticipate that -3 is along the y-axis, a diameter of 3, but in the negative direction. So I think we actually do have that one happening over here. So like that. +3 would have a diameter of 3 in the positive direction. Sine is along the y-axis. And you might remember that when we're talking about ordered pairs of points, when we're talking about cosine and sine anyway, like with our unit circle, it goes cosine first and then sine. This is like your x coordinate. This is your y. That might help you remember which axis these are symmetrical around. So these are circles. Hopefully you notice that cosine is symmetrical around the x-axis, and sine is symmetrical around the y-axis. And if we think of this in the form of y equals a cosine of theta or y equals a sine of theta, where a is some constant multiplier in the front, a is the diameter of the circle. I'm going to go ahead and stop this video here so it doesn't get too long. And then I will continue with another video as we continue moving through the packet. Thank you.